Okay, hello everyone. We are going to be talking about chapter 3, which is the derivatives. We will go through the section. There are 86 pages. We'll go through the necessary pages that we require. You're going to see that. Section 3.1 is about tangent lines and the derivative at a point. Tangent lines, we discussed tangent lines before, but derivative at a point we have not discussed yet. Okay, so let's say the blue one is our curve, y is equal to f of x, and we are interested in finding the tangent line to the curve at the point p x0 f of x0. That's the only question to answer, okay? Find the tangent line equation to the curve at the point P. Okay, so how are we going to answer that? First of all, if you want to find the tangent line equation, you need the slope of the tangent line and you need a point on the line. This point is already given. P x0 f of x0, this is given. The only thing that is missing is the slope of this tangent line. And in the previous sections, chapters, actually chapter 2, we said that we can find the slope of this tangent line, right? Approximately. We would just take this Q, make it closer and closer to P, and then SQ gets very close to P. We would just compute the slope of the secant line. This black one is the secant line, and you would get each time you get this Q get close to P, you get a different secant line, and you would calculate the slope of that secant line, and you're gonna look at all these slopes that you get for each secant line, and they are going to converge to the tangent line, slope of the tangent line you have. So how would you write the slope of this secant line, the black line? Secant line means there are more than 2 points. You just combine these 2 points and you get a secant line. Okay? Tangent line, just it crosses the blue curve at 1 point. Secant line crosses the blue curve at 2 points. Now, how would you find the slope of the secant line? You would just take the difference between the y values, which is f of x0 plus h minus f of x0 over the difference between the x coordinates of these points. So x0 plus h minus x0, x0s are going to cancel, we have h. So this thing that you're seeing is the slope of the secant line. But we take the limit as h goes to 0. The reason is we are thinking about infinitely many secant lines here that are, and each time we are getting more and more close to the P, and you just take the limit of the slopes. So it's slope, and you take the limit of the slopes as h goes to 0. H goes to 0 means x0 plus h is going to get close to x0, right? And this is the formulation of the slope of the tangent line at the point P. Okay? Good. So this picture is really useful. If you understand this picture, you are good to go. So, since we understand the geometry behind it, now we can define it. So the slope of the curve y is equal to f of x at the point P x0 f of x0 is just the limit as h goes to 0, f of x0 plus h minus f of x0 all over h. Of course, as long as this limit exists, then the slope of the curve exists, and it is this expression. Okay? And then, if you're interested in the equation of the tangent line, this is the slope of the tangent line, and you already have the point. You just write the tangent line equation like that. So no problem. So slope is the only missing part. Okay. Then let's look at some examples. You remember these examples. This is the example. This is the butterfly example. Look at that. These are just wings of the butterfly, right? And this is famous function y is equal to 1 over x. Okay, we are interested in the slope of this 1 over x at a point A. A is just an arbitrary point A. what you do is you just take this 1 over x, put it in the equation, limit definition that we have seen, and you will get negative 1 over a squared. Okay, and if you're interested in finding the slope at negative 1, you just put negative 1 instead of a. Negative 1 squared is 1, negative 1, so the slope at x is equal to negative 1 is negative 1. And you see this line is actually has a slope negative 1. Okay. Alright, this is a nice example actually. But you can ask me how we found it. We just put it in, and at the end of my talk I'm gonna do it actually on whiteboard. Okay, maybe we can just stop. Yeah, I'm gonna do that at the end. Okay, you're gonna understand it. You just need to look at the end of the lecture here. This is just again the butterfly example, 1 over x. We just put in. For example, this is the point P, 2 to 1 over 2, and the slope is going to be what? Negative 1 over a squared. A is 2, so it's going to be negative 1 over 4. And let's take another point on this side of this butterfly example, and at this point P, negative 2 to negative 1 over 2, and the slope is negative 1 over a squared. A is negative 2. Take the square of negative 2, you get 4, negative 1 over 4. Okay, so this is you got this easily. And then, okay, this is good because look, as you change, if you go back to the previous example, as you change the x value, you get different slopes, right? Because if you take a point here, you get a different tangent line. If you move to this point, you get a different tangent line. And of course, different slope. Let's say if you take this point, you get a different tangent line. So if you do that, then this is going to tell you, actually, since as you change the point, you get a different slope, then you can really look at the slope, the limit definition of the slope as a function. That's what we are going to do next. So actually this, you could see this as a derivative of a function of f. Oh, okay, no, I'm sorry. I was talking about considering this as a function. Or you can see it like that here too. First of all, we call it as the derivative of a function f at a point x0. If you know f prime x0, so this is just to give it a different name. Before we would call it the slope of the tangent line, but we give it a different name, general name, which is the derivative of function f at the point x0. Another thing is actually as x0 changes, this value changes, we can look at it as a function. Okay, so the derivative, you can look at the derivative as a function. Okay, but before we do that, let's repeat what we just talked about. This is called the difference quotient. This is, and then you put the limit in the front. So limits as h goes to 0 of the difference quotient has many interpretations. We have talked about it before. Let's repeat it for you again. For example, one meaning of this is, if you are considering y is equal to f of x, the function, and the graph of it, it is the slope of that function at the point x is equal to x0. Okay. Second interpretation. Okay, again you have the same curve, y is equal to f of x, and of course at x0 there's a tangent line to the curve, and what we have found is the slope of that tangent line to the curve. Another interpretation is we can look at this difference quotient as a rate of change of f of x with respect to x at x is equal to x0. Okay, limit of that quotient. And then lastly we have said that let's give it a name, and we gave the name the derivative f prime at x0 to this x limit expression. We gave that name. All right. Okay. Next section. This is the part that I wanted to actually talk earlier. You can see this derivative as a function, which I mentioned this to you as well. Because as we change x, of course, the value, the slope is gonna change. Because as you change x point, you're gonna get a different tangent line, right? At different x's, you get a different tangent line. Since you have a different tangent line, you have different slopes. So therefore, actually, since you are getting different slopes for each x, we can consider this as a function. So you can see, and this is the derivative, right? You can see derivative as a function now, function of x. Of course, excuse me. In each definition, we always want that this is a limit. This limit exists. Okay. If this limit doesn't exist, then it doesn't make sense. Okay. So this is another picture that explains the situation. The blue one is our f of x, and then the yellow one is our secant, and then we can find the slope of the secant as f of z minus f of x over z minus x. Why is that? Because if we just let this point x, if we let this x plus h as z, and then this is going to be f of x, this is going to be f of z, so f of z minus f of x over z minus x is going to give you the same thing. It is a difference quotient again. It's equivalent to that. So this difference quotient is the same as this difference quotient, but look at that. Here we are using x and h, and we let h goes to 0. This is the definition of the derivative we just talked about of f at the point x, but this is going to be the same as this difference quotient as z goes to x. Alright, so there are two ways of expressing the same thing. You can use whichever you like, whichever is easy for you, and therefore we call this definition as alternative formula for the derivative. Alright, okay, let's give it a try. Let's have our f of x to be root function, square root of x, and the blue one is the graph of the square root of x, which you are familiar. We talked about this before, and we are interested in the slope of the tangent line to the curve at 4. So this is 1 over 4x plus 1. Why is that? First of all, you're going to take the derivative of the square root of x, but for this we have to use the limit definition of f prime of x, and then you're going to get, okay, you're going to find the slope as 1 over 4. If you do that, if you evaluate that f prime at 4 by using limit definition, you get 1 over 4, and then you're going to just use the point and the slope. You get this tangent line equation for that. So if at the end of this lecture, actually I can do that square root of x as well, example as well. Alright, so let's see. This explains actually rate of change of f being negative, positive when it's going down and up. So here's we have the blue one. It's good to talk about it. Okay, this blue one is our f of x, and then we just choose some points where we have the slopes, tangent lines and their slopes. For example, at A, this is a horizontal tangent line, so the slope is 0. At B, this is not a horizontal tangent line. Okay, this has slope negative, obviously. At C, we have a negative slope as well. Okay, and then at D, slope is 0 because we have a horizontal tangent line. At E, we have a positive slope because our tangent line is going up like this. These are all approximate values. You can just since we have this these numbers are given, you just approximate it. Look at that. Like if you consider here, this is like 10 over 10, let's see, 5 over 5, so it's negative, so it's -1. This is a little bit steep, so this is bigger than this, so therefore it's -4 over 3. And look at this one. This is going to be this triangle 8 over 4, and you're going to get 2 at E. The slope is going to be 2 at E. Okay. Okay. So let's see. This is the graph of f prime at x. So you have the graph of f, and then you just want to draw the graph of f prime at x. Now the slope is 0, which means the derivative is 0. So the derivative is 0 at a. I mean the corresponding x value, whatever this is, we call it a prime here. Okay, it's going to be 0. That's why we have it crosses the x-axis at 0. This is f prime, by the way. Okay. And we also have at d, the slope is 0, so d prime has to pass through, d prime has to be on the x-axis too, because this is showing the graph of slopes. Okay. And then we have a negative slope here. That means at b, which is b prime, that's the corresponding one, the value has to be -1 here. And at c it is -1/4. -1/4 is going to be less than -1, so it is right here. And then e is a positive value, so it has to be above the x-axis, and it is 2. So you just combine these guys and you get the graph of f prime at x. Okay, so these two things are different, and you draw this by using this picture and just looking at the slopes being positive or negative. You draw this being 0, you just draw that. The best thing is to start drawing the zeros first, and then the others carefully just plot them and then combine these graph. Okay, alright, good. Let's see. Okay, okay, alright, so we have seen derivatives inside an interval. Now we are going to be talking about the derivatives at the end of the interval. Okay, derivatives at the end of a closed interval. Okay, so these are going to be one-sided limits, as it shows here. For example, we are interested in derivative at the point b. What is this? So we can define it in terms of one-sided limits, because we don't have anything on the right-hand side. So limit as h goes to 0 from the left, alright? So fb plus h minus f of b over h. We let this to be 0 from the left, negative values of h, because we are writing fb plus h here, right? In order to have to the left of b, h has to go to 0 from the left. On the other hand, if you look at a, so we are going to be approaching a from the right. So our h is going to be taking positive values. Fa plus h is going to be here, a minus f of a over h. Alright, so now we have seen so far derivatives at an arbitrary point or derivatives at the end points of a closed interval. We have seen it, and they are one-sided limits. Be careful about that. Okay, so we want to see an example. This absolute value of x, this is a very important example. So I want you, simple example, very important example. So I want you to keep this in mind, okay? So absolute value of x, we talked about that. It's a V-shaped graph. Look at this V. Very nice, right? This is a V-shaped graph, and we are interested in the derivative of this function. Okay, so this function is a piecewise function. It's made up of two pieces, this piece and this piece. Actually, this piece has x and this piece is negative x. Now, what you could do, you could use the limit definition, and then you can show that y prime is equal to 1 on this along this curve, and y prime is equal to -1 along this curve. I will do that at the end of this lecture as well on whiteboard. This is an important example. This is our third example that's important, okay? I have to do that on whiteboard. Okay, and actually you can find those in my lecture notes as well. I put them on, there are some, right, I put my handwritten lecture notes. You'll be able to see all these clearly explained in my handwritten lecture notes. I put them online from last semester, okay? Please take a look at those lecture notes as well. Okay, the problem here is what happens at 0. At 0, the derivative does not exist. The reason is, if you look at to the right of 0, the derivative becomes 1. If you look at the to the left of 0, the derivative becomes -1. So they don't agree. So at 0, to the left or to the right, they don't agree. So there's no way at 0 we are going to have a derivative, okay? Because of that, it doesn't exist. We usually call it as a corner. So if you have a corner in the graph, don't expect to have the derivative defined at that point, all right? So we call it this function y is equal to square root of x, y equals the absolute value of x, I'm so sorry, is differentiable everywhere except x is equal to 0. That's what we are going to call. There's only one point that y is equal to the absolute value of x is not differentiable at. For the rest of the points, it is differentiable. Okay, let me see. Next page. Okay, let's go back to square root function again. Now for square root of x, everywhere except 0, okay, and the function, the graph of the function behaves really nice. So it has a tangent line here, it is a tangent line here, it is a tangent line here, but at 0 it doesn't have the derivative. So here we have to look at the one-sided limit definition of the derivative, which is limit as h goes to 0 plus from the right, f of x plus h, f of 0 plus h minus f of 0 over h. Okay, f of 0 plus h is square root of h, minus f of 0 is 0, square root of h over h. So what is the limit as h goes to 0? Square root of h over h. Square root of h over h is the same as 1 over square root of h. Limit as h goes to 0, 1 over square root of h does not exist because h, the denominator, makes it undefined because h goes to 0. So there's no way that at 0 we have the derivative of this function. So forget it. So this function is differentiable everywhere except at 0. Okay, so there are a couple of situations when you look at the graph. You can easily see that it is differentiable or not. Okay.